So I'm assuming everybody wants to talk about chapter 6 and 7 because we have a quiz tomorrow on it. Okay. So for those of you that were here last week, we did go over 6 and 7, and we mainly focused on this chart here, which is the last page in Dr. Cosper's notes. It came to my attention today when I was working with a couple students that this chart can be actually a little misleading, and if you reviewed Dr. Fred's notes closely or read the chapter, you may notice some issues with E2 elimination by molecular. So I tried to kind of rearrange this chart in a way that kind of emphasized that although this isn't incorrect necessarily, it's a little misleading the way that it's written. So I wanted to first start by kind of talking about that, and then we'll review each of the individual reactions themselves. So I know this definitely isn't as pretty, and I don't know if, can you guys even see the bottom part now? Mm-hmm. Okay. So basically, I want to kind of talk about why we had to make some changes. So E2 we had with a primary alkyl halide, a strong base, a large nucleophile. That is true. That does occur, but E2 reactions actually perform better with secondary or tertiary alkyl halides. The only time it will work with primary is when you have this strong base with a large nucleophile. But again, that's only one small instance. The vast majority of the time, an E2 mechanism prefers a secondary or a tertiary alkyl halide. Everything else, it has gone unchanged. The type of solvent, the stereo specific, concerted, all of that is still the same. It's really just this one piece on alkyl halide classification. Does everybody kind of, I know those of you that weren't here last week, we haven't gone over each individual piece. We will go over that. But for those of you that maybe have reviewed this material, do you understand this chart, how I've made these changes? No, you're still drawing and not really processing, but.
So, secondary alkyl halides can only do E2?
No. So this isn't perfect. But the way I tried to write it, because there's no way to perfectly write it in one chart, this is kind of the fastest. Okay, so SN2 can also, they actually all can use secondary, but it runs fastest with primary. SN1 and E1 can use secondary, but run fastest with tertiary.
So this is like the preferred chart.
Exactly.
Okay.
Keep writing down that stuff, but this is basically what I just said. So each of these mechanisms, and then here we have the classifications of alkyl halides that can perform, and this is actually straight from Dr. Fred's notes. So SN2 can use primary and secondary only. They do not run with tertiary. SN1 and E1 use secondary and tertiary. They do not use primary. And then E2 can technically use all of them, with tertiary being the most favored, primary being the least favored, because again, primary would only occur if you had this specific nucleophile reacting. It wouldn't, otherwise, if you had primary, it would always go to SN2. It would be a substitution, not an elimination. I know that's confusing and goes against everything that we talked about last week, so I apologize.
In the bottom row, that's the products that we get?
Yep, and the products haven't changed. Again, the only thing that's changed, I've added a middle row, and I put E2 there and made E2 in this box smaller just to kind of reinforce that it really doesn't occur that often. Everything else around the outside has stayed the same. Any other questions about this or that one change? We are going to go into all the specifics again. Yes?
Can you just explain that chart one more time?
Absolutely, yeah. So for each of these mechanisms, these are the classification of alkyl halides that will undergo that mechanism. So in an SN2 mechanism, you can have either primary or secondary, but not tertiary. For SN1 and E1, you can have either secondary or tertiary, but not primary. And then for E2, you can technically, any of them, under the right circumstances, can undergo E2, but you're more likely to get E2 with a tertiary, and you're least likely to get it with a primary. Yeah. Okay, can we go into the specifics of each one? I am going to flip back just because the other one it's a little better oriented. This one was kind of a hack job, but okay. So I was going to just go through like I did last week, talk about each of these mechanisms and the characteristics that are involved in that mechanism. It may be a little bit of a repeat for those of you that were here last week, but don't be afraid to stop and ask questions. So again, this chart really is still useful. It's just you got to be careful with the E2 when you're studying. But otherwise, the other three reactions, this chart works really well for. It's very well organized. I usually recommend that students kind of throw this on their quiz when they get it, just so they can kind of refer back to it as you go through your quiz. You don't have to have all of the information written down, but definitely have an understanding of what's involved. And the only thing that's really not on here is the why. So that's what we're going to talk a lot about today. So primary is here for SN2, but why primary and not something else? Okay? So let's start with SN2. So what does SN2 stand for? Oh, come on. Okay. Nucleophilic.
Bimolecular.
Okay, what does bimolecular mean? Somebody other than, I'm sorry, I forget your name. Somebody other than Kate.
Concentrations of two reactants that affects the reaction rate.
Good. So second order reaction. So concentration of two. Influence reaction rate. Okay, so that in a bimolecular reaction would be the concentration of the alkyl halide and the nucleophile. We're later going to talk about SN1 and E1, which are unimolecular. So obviously, it's the same thing except one reactant influences the rate. For unimolecular reaction, is it the concentration of the alkyl halide or the concentration of the nucleophile that affects reaction rate? It's the alkyl halide. Okay, so again, we'll talk about this when we get to unimolecular, but in unimolecular reactions, the concentration of the nucleophile doesn't affect the reaction rate. Okay? All right. Wondering. I can always just erase this now. Okay, so here we have a primary alkyl halide. Does anybody remember why a primary alkyl halide is preferred for an SN2 reaction? I'll put this back up later.
Doesn't it allow the nucleophile to get into the carbon?
Good. So basically, if you were to have tertiary, okay, there'd be big bulky groups in the way. So there's a term for that you guys have talked about a lot. Starts with an S. Steric hindrance. Very good. So I'm going to just draw the picture that's on Dr. Cosper's, just so we can get a better look at it. Okay, so here we have the nucleophile attacking the opposite side of the halogen. So it's always going to attack the carbon that is attached to the halogen, and it's always going to attack in this direction. So we call that a backside attack, okay? It's on the backside of where the halogen is connected. That is something that he could ask you. So because this nucleophile has to fit into this carbon in the center, there has to be space there to do that. If we were to have a tertiary, I'm just going to draw big bulky methyl groups here, it's a lot harder for the nucleophile to get in to attack that center carbon. Okay? So we need a primary alkyl halide in this case because of steric hindrance. Is an SN2 reaction, does that take place in one step or more than one step? It is one step. So if we were to draw, don't have enough space. Sorry, guys. Okay, so why have I drawn dotted lines between the nucleophile and the carbon and the halogen? So this bond is being formed. At the same time, this bond is being broken. There's a word that he uses that you need to know. What is it called when you have bonds being formed and broken at the same time? Concerted. Okay. When a reaction is concerted, that means it has a transition state. That's what I'm showing here, the transition state. So we have this midpoint between our reactants and our final product. But it's not actually a step. It all happens, you know, at one time. There's not multiple steps taking place. When the halogen is removed, this ends up being our final product. So we've substituted the nucleophile for our halogen in this case. So let's take a step back. Here when I showed the nucleophile attacking the alkyl halide, I only drew one arrow. That was intentional. The nucleophile can only attack the carbon at this one attack spot, so it can only perform a backside attack. It can't attack anywhere else. There is a term for that that you've talked about in lecture. If the reaction is only taking place at one place, that reaction is stereospecific. Okay? You can think of specific, so specific spot, right? So the reaction's taking place at a specific place, so it's stereospecific. That is important, especially for this reaction. It affects the absolute configuration, which is a little bit of a throwback. If I were to ask to find the absolute configuration of our alkyl halide, okay? Absolute configuration has to do with molecular weight, or sorry, atomic weight. So you want to find the attachment that has the highest atomic weight. And our alkyl halide, what would that be? The halogen. Now I know it's hard because we don't have a specific halogen, but if we think about the periodic table, even our smallest halogen has a higher molecular weight than carbon, okay? So our halogen would be the highest molecular weight, then our carbon, and then our two hydrogens would be the next. So for absolute configuration, you start at 1, go to 2, keep going all the way around. So this is clockwise. Is that R or S? R. Okay. Now if we look at our final product, again, we don't know exactly what our nucleophile is, but nearly every nucleophile is going to be larger than carbon. So we can give the nucleophile a number 1, carbon number 2 again, start at number 1, go to number 2, go all the way around. Counterclockwise would be S. So why am I showing you this? Chances are he will probably ask you about this, okay? So essentially what I've shown you, if you start with R, after you go through an SN2 reaction, your final product is going to have an S configuration. If you start with an S configuration, your final product is going to have an R configuration. That's going to happen every time you have an SN2 reaction. You're always going to flip-flop. And that is because it's stereospecific. If the reaction could take place at multiple points, you wouldn't have that nice pattern going on, okay? So, and I talked about the classification of the alkyl halide. I didn't really talk about the nucleophile, but basically the reasoning for both of them is nearly identical. So again, we talked about how this nucleophile is coming in and attacking that center carbon. In order to do that, you have to have a small nucleophile. If you have a big nucleophile, it's going to be sterically hindered, and the reaction isn't going to take place. So small nucleophile, primary alkyl halide. There's a concerted reaction with a transition state, and it's stereospecific, meaning that the absolute configuration is going to switch. What did I forget? Oh. I didn't talk about the leaving group here, but this is really the same for all 4 reactions. Who remembers what the best leaving group is? No. Iodine. So when we're talking about our halogens, okay, this kind of goes back to when you were talking about the strength of acids. So things that affect how strong an acid is, it's either size or electronegativity. When we're talking about our halogens, the electronegativity is very, very similar. Fluorine is technically the highest, but halogens are all very electronegative. So it really comes down to size. As you go down the periodic table, size increases. Iodine is drastically larger than fluorine is. So iodine is going to fall off and leave more readily than fluorine. So iodine is considered the best leaving group. That is very important. He will definitely ask you that. And that corresponds to any of these reactions. Whether you're talking about SN2 or E1, iodine is always considered the best leaving group. Solvent. Didn't talk about solvent. Okay. So the type of solvent that this reaction is taking place in is important. For an SN2 reaction, we prefer what's called a polar aprotic solvent. So last week we talked about what aprotic meant. Does anybody remember what aprotic meant? Protic means proton. And proton really just means an H+ ion. So if you're aprotic, that means you don't donate H+ ions. Okay? Likewise, if we had a protic solvent, it does donate H+ ions. So for SN2, we want polar aprotic. Okay? Now, the reasoning why. So again, this is our reaction taking place. We have a negative nucleophile floating around in this system. If we have H+ ions in the solvent, it's going to tie up this nucleophile and make it less able to attack the alkyl halide. So we don't want protons tying up this nucleophile. So polar aprotic is wanted. Okay, we don't want these. Any questions on anything I just threw at you? All right, let's do a quick recap. So SN2 stands for substitution nucleophilic bimolecular, meaning that the concentrations of both the alkyl halide and the nucleophile affect the reaction rate. For an SN2 reaction, you prefer a primary haloalkane because you want to reduce steric hindrance, and a small nucleophile to reduce steric hindrance. This reaction prefers polar aprotic solvents because you don't want protons tying up the nucleophile. It's stereospecific because the nucleophile performs a backside attack. Actually put that here. It's concerted, meaning bonds are being broken and formed at the same time and a transition state is formed. If you start with an R alkyl halide, you end up with an S final product, or vice versa. And your final product is just the nucleophile substituted for whatever your halogen is. Any questions? Okay. Let's move on to E2. Again, remembering this. I know Dr. Cosper's notes don't necessarily show this, so just keep this in mind. Okay. So I know, and how about this? I'll fix this while I'm here. I know in her notes she has a primary alkyl halide. I'm going to just use tertiary just so you can get more familiar with seeing that. Because again, secondary and tertiary are prefer an E2 reaction for this one. So the first thing I want you to notice is where the reaction is taking place. So in an SN2 reaction, the nucleophile was attacking the carbon attached to the halogen. You can see in this case, it's actually attacking these outer hydrogens. We still have a concerted reaction that hasn't changed because it is bimolecular. But you'll notice there's a lot more, forming and breaking of bonds. So I've drawn, I don't know if you can see it in the back, but the red is illustrating bonds being formed. The black are bonds being broken. So essentially this nucleophile is bonding with this hydrogen. So it's going to break the bond between the hydrogen and the carbon. The halogen is going to fall off, so breaking this bond here. When we pull the hydrogen off and pull the halogen off, we leave each of these carbons with 3 bonds, so that's going to drive a double bond to form. Okay, that's why our final product for an elimination reaction are alkenes. Okay. I just realized that we never went over what E2 stands for. So E2 stands for elimination bimolecular. Elimination reactions always make alkenes, which you can see in the chart there. So let's talk about some of the similarities. So all of the things on the right side, so the type of solvent, the fact that it's stereospecific, the fact that it's concerted and has a transition state, those all apply to both SN2 and E2 reactions. So really what we're changing here is now the alkyl halide and the type of nucleophile in the final product. So instead of a small nucleophile, this reaction prefers a large or bulky nucleophile. And that really has to do with where the reaction is taking place. Because we don't have to attack inside of the center carbon, we don't need to worry about having a small nucleophile. It's attacking these hydrogens on the periphery, so it's okay to be large and bulky. We're not worried about steric hindrance here. This is a change from last week. I know that we talked about preferring primary, but again, based off of notes and the textbook, even though an E2 reaction can use any size or any classification of alkyl halide, it does tend to prefer secondary or tertiary, so that's something new to think about. What am I forgetting? I don't think I'm forgetting anything. Oh, yes I am. So it is stereospecific, but it's not considered a backside attack. Now, I've only drawn one arrow here, and again, it is specific to this hydrogen. So the hydrogen that's going to be attacked is always going to be on the opposite side of the halogen. This is considered a top side attack. So SN2 was backside, E2 is considered top side. Okay. I know this one is a tough one because I changed it up from last week. Do you guys have any questions? Yes.
So say that our X representation
Yes.
is where the methyl group is. Would it still be considered topside attack if it has to be opposite?
Oh, so you're saying like switch this and this?
Yeah.
So really we're just, so imagine technically you're just rotating it, right? So you're not really changing. So I could rotate this and have the halogen up here, but that would be exactly the same molecule as having it down here.
Okay, I get what you're saying.
Yeah, so yeah, I can understand. Technically it would be a bottom side attack, but if we just reoriented the molecule, the point is it is always going to be on the opposite side of the halogen. So if I were to flip this, it would technically be bottom side, but this is how you should think about it. Yes?
So, do you think he's going to ask us what it's going to be primary, secondary, or tertiary for this? Or it could be either?
Right. So the moral of the story is it's going to depend on the other aspects that are happening. And so that's going to, Of course, I erased that part, so maybe I'll rewrite it really quick. So for example, oh, those were fraction substitution. It doesn't apply to E2. So for primary, the only time you'll have an E2 mechanism is when you have a strong, large nucleophile. That's the only situation that that will occur in. If you have any other type of nucleophile with a primary, it's going to go to substitution. When we're talking about these, you can have a varying, depending on the size of the nucleophile, depending on this here, it will drive E2. So I don't think he's going to get into the specifics of that. I just think, if he says, for example, if he gives you a scenario that uses secondary and he specifies a specific type of nucleophile, you should be able to determine which ones are possible. So there may not be one specific answer, I guess is the best way to put it. You could have, some with SN2 and some with E2, depending on the type of nucleophile that's being used. Okay? We're going to talk a little bit about how secondary can affect SN2 and SN1. I think with E2, what you have to be careful with is if he says, for an E2 mechanism, what classification of alkyl halide would be most preferred? That would be tertiary in that sense. Because tertiary, I had it written up there before. For E2, primary is the least, then secondary, then tertiary. So he could ask about that. This was in his notes. I didn't write down the page, but so I think if he's going to ask you about E2, it's going to be asking which of these would be favored for that mechanism, and in this case it would be tertiary. But for SN2 and SN1, we're going to talk about how secondary can go one or the other depending on some other characteristics. Sorry, I know it's kind of a confusing answer. Any other questions for E2 before we move on to E1? Okay. Okay, so things really start to switch up for SN1 and E1. So we kind of talked about unimolecular already. So unimolecular just refers to a first order reaction rate. So the reaction rate is determined by only one of the reactants, not two. Okay, for those of you that were here last week, we talked about how in SN1 and E1, the first step is considered the rate determining step. Okay. Now, step one, you have your alkyl halide, and the halogen removes itself. So we have the halogen coming off, and that forms a carbocation. So because we know that step one is the rate determining step, we know that the concentration of the alkyl halide is what affects our reaction rate. So depending on how quickly the halogen removes itself, that determines the entire rate of the reaction. So if we have a good leaving group like iodine, this entire reaction will take place very quickly. If we have a poor leaving group like fluorine, the entire reaction will be slowed down. So the rate is only determined by the concentration of your alkyl halide. The concentration of the nucleophile has no influence on the reaction rate. Everybody good with that? Okay. So I said this first step forms our carbocation. So again, a carbocation, you may recognize that it kind of looks pretty similar to a carbon-free radical, and they actually are both very similar. So instead of a free radical which has one lone electron, we have a carbon that has lost both of its electrons, so it has a positive charge here. And so we have this sp hybridized orbital here with a positive charge that can react with a nucleophile. One thing I don't think we talked about last week, we may have or not specifically, but he could ask you about the orbital hybridization of this carbocation. So does anybody know what, so when I say orbital hybridization, I mean sp1, sp2, sp3. So what would the orbital hybridization of this carbon be? sp2, okay. Who wants me to go over how you figure that out?
Can you go over your trick?
Okay, yes. So when you're talking about carbons, I will say when we get to oxygen, like in chapter 8, it does get a little trickier. When you're talking about carbons, because they typically show all of their bonds, all you have to do is count the number of attachments, okay? So let's start with this one, just as an example. So this carbon has 1, 2, 3, 4 attachments, okay? For a bit of refreshment on orbitals, in each energy level, you have 1 s orbital and 3 p orbitals. So with your number of attachments, you count 1 s, and then you count up the p's. So 1, 2, 3, 4. This is an sp3 carbon. Okay? If we were to go back to this one here, so this carbon has 1, 2, 3 attachments. So s, and then p, 1, 2, 3, sp2. We look at an alkene. This is where I like to clarify, when I say attachments, I don't necessarily mean bonds, okay? Because a carbon will typically have 4 bonds unless you have something like this. So this carbon, even though it has 4 bonds, has 1, 2, 3 attachments. So it would still be considered sp2. And then one final example, we have an alkyne. This carbon has 4 bonds, but has 1, 2 attachments. So 2 attachments, sp1. Does that make sense? Okay. Can I erase the orbital hybridization stuff? Okay. So he could ask you what the orbital hybridization is of the carbocation. He probably won't ask you about the other molecules, but just be ready for that. Okay, so we form our carbocation. And again, this carbon has 3 bonds right now, which means it's pretty reactive. It wants to make that 4th bond. So we have a positive carbon, and we have a negative nucleophile running around. So this nucleophile is going to be drawn to that carbocation. You'll notice that I have one arrow up going towards the top, one going towards the bottom. Would this reaction be considered stereospecific or not stereospecific? Not stereospecific, because we can have an attack from the top, an attack from the bottom. I think in his notes, he wrote something along the lines of, above or below the P, but like that's all he wrote. That's all he's saying here. So top or bottom of that carbon can be attacked, which means you're going to end up with 2 different types of final products. So they look very similar, but technically they would have different conformations. So if we have half of our nucleophiles attacking the top and half of them attacking the bottom, okay, we'd have 50% of each of these. So let's say that this molecule rotates light dextrorotary, I know I'm saying that wrong, and this one rotates light levorotary, okay? What type of mixture will be created? Racemic. You have 50% that's rotating light clockwise, 50% rotating it counterclockwise. So together that creates a racemic non-active mixture. Everybody with me there? Okay. I think actually that was, did I write it on this one? I did, racemic. Okay. So, all right, let's take a step back here. So we know that tertiary haloalkanes are preferred for SN1 and E1. Who remembers why? Why do I have a tertiary here? Why not primary? Most stable carbocation. Thank you. Yes. So tertiary carbocations are the most stable and they're the easiest to form. Okay. So again, secondary haloalkanes could be used for this reaction. It is going to run a little bit slower. Primary is not going to work here at all because the primary carbocations are so unstable and so difficult to form. Okay, in terms of the nucleophile, again, when we were talking about SN2, so the point of attack is really the same for both SN reactions. We're trying to attack this center carbon that was attached to the halogen. So to be able to get into that center carbon, the nucleophile still has to be small. If we have a big bulky nucleophile, there's going to be too much steric hindrance to attack that center carbon. So that really hasn't changed at all. We already talked about how it's not stereospecific, but we really haven't talked about the solvent. So for unimolecular reactions, we prefer polar protic. Last week we kind of talked about a couple different reasons why polar protics are preferred. In your notes and in Dr. Fred's notes, he really emphasizes the fact that the ions, so the protons and other ions, that are in the system, help form and stabilize the carbocation. So that's really the number one reason. But another way to think of it that kind of helps me remember it, so when we were talking about SN2 reactions, we were really concerned with these H+ ions tying up our nucleophile. So if that were to happen in this reaction, if the protons were tying up this nucleophile, we really wouldn't have to worry about it because the concentration of the nucleophile doesn't affect the reaction rate. The reaction rate is solely based off of the concentration of this alkyl halide. So even if some of our nucleophile gets tied up and we can't necessarily use it, the reaction is still going to run, like the reaction rate isn't going to be affected. So definitely know that it helps form and stabilize, but just another way to think of it is, who cares if that nucleophile is tied up? We don't necessarily need to worry about that. We talked about that it's not stereospecific. We have two different points of attack. It is stepwise, so step 1, step 2, it's not concerted, and it does have this carbocation intermediate. I think that basically covers everything there. Any questions on SN1? Okay. I do want to quickly talk about so when we have a secondary alkyl halide, okay, and we're talking about, is it going to go SN1 or SN2? Because it can be used in both. There are a couple things that you can keep in mind. So for an SN1 to take place, you need to have a very good leaving group. LG is leaving group. For an SN2, you only need a good leaving group. And again, that makes sense. So if we have a secondary now instead of tertiary, we know that this carbocation is going to be slightly harder to form. It's going to be slightly less stable. So we need a really good leaving group that's going to kind of push this to form. Okay, if we have an okay leaving group, the carbocation isn't going to want to form because, again, it's going to take a little bit more energy just to get it to this point here. So for an SN1, we need a very good leaving group. For SN1, when we're talking about the nucleophile, it's okay to have a poor nucleophile. For SN2, we need a strong nucleophile. And we really need a large concentration of the nucleophile. Again, this piece makes sense. We need a lot more nucleophile because in SN2, the concentration of the nucleophile is going to help determine the reaction rate. And then in terms of the solvent, Aprotic is going to drive SN1, Aprotic is going to drive SN2. But you already know that. So these were three characteristics that could determine whether something goes SN1 or SN2 if you have a secondary. So if you're in kind of that gray zone and he gives you some of this information, you can know if the reaction is going to go SN1 or SN2. Was there a question?
Yeah, I got it. Thank you.
Okay.
I just didn't know what LFG is.
Oh, leaving group. Yeah, sorry. Okay. I think that covers everything for SN1. Did I miss anything or does anybody have any follow-up questions? Can move on to E1. Okay. Okay, so E1, again, elimination. So for elimination reactions, we know that our final product is going to be an alkene. You'll also notice that I didn't change anything. I just rewrote a tertiary because that's technically what would be most preferred. Nothing changes in this step one. It's identical when you're looking at the steps. So step one is still the rate determining step. The halogen falls off, creating our carbocation. That has not changed. The first thing that really has changed is the size of the nucleophile and where it's attacking. So just like when we were talking about E2, we're no longer worried about attacking the center carbon. We're now attacking the peripheral hydrogens, and we have three different options in this case. So you'll notice the three different arrows, meaning that this reaction is not stereospecific. It can pick from any one of those. Once we remove one of those hydrogens, you'll have this carbon who only has 3 bonds already, and this carbon will then only have 3 bonds. So that's what drives this carbon-carbon bond, creating our alkene. The type of solvent hasn't changed. It's still stepwise. We still have a carbocation. We still want a tertiary alkyl halide. The only thing that has changed is the size of the nucleophile and where we're attacking the carbocation. Any questions? Kind of flew through that. We still have 15 minutes.
Is there a reason if we use a Aprotic solvent in this one that that second carbon doesn't just pick up a hydrogen from the solvent?
Thank you.
Yeah, no problem. You're saying right here?
Yeah. Instead of driving the double bond?
Oh, I see what you're saying. Honestly, I'm not sure if that is something of concern. I'd probably have to look into the textbook. With all of these, it's important to know that they're, even when we're looking at 2 different mechanisms, you know, if we have a primary or a tertiary haloalkane, like 25% of the product could be, you know, our elimination alkene and that's 75% of it. So there's always a chance for products that we don't necessarily want.
Okay.
But that is a good point. That could possibly happen. Any other questions? People that maybe weren't here last week, anything that I might have gone too quickly over, might have taken for granted? Okay, I mean, we still have 15 minutes. Is there something else you'd like to go over? Talk about chapter 8? End early? What do you guys want to do? I suppose I could ask questions. We kind of did that a little bit last week. Would that people like that? Like maybe like a different kinds of questions? Let me see. Okay. What's the final product of an elimination reaction? Alkenes. What's the best leaving group? Iodine. For an SN1 reaction, would you rather have a primary, secondary, or tertiary alkyl halide? Tertiary. I said SN1, right?
Oh.
Sorry, that was kind of a long question, and you can't read it, so it's hard to remember everything I'm saying. If you have a big bulky nucleophile and a primary haloalkane, what mechanism will be used most likely? So I said primary haloalkane and big bulky nucleophile. E2, very good. What do polar Aprotic solvents donate to the system? Protons, specifically. Ions would, it's technically correct, but it's too general. Out of the 4 different reactions, which are considered stereospecific? If you have a... That's another question. If you have a small nucleophile and a tertiary alkyl halide, what is the preferred mechanism? Small and tertiary. SN1. Good. If in a reaction bonds are broken and formed at the same time, that reaction is considered concerted. Out of the 2 steps in an E1 reaction, which is considered the rate determining step? In an SN1 reaction, we cut the concentration of the nucleophile in half. What will happen to the reaction rate? Anybody else? It doesn't affect it. So we're talking about an SN1 reaction, right? So unimolecular, the reaction rate is only based off of the concentration of the alkyl halide, and I cut the concentration of the nucleophile, so nothing would happen. What's the orbital hybridization of a carbocation? sp2. What type of mixture is created in an SN1 reaction? If you have, so in an SN2 reaction, your starting product is an R absolute configuration. What is your final product? I don't think I have any more questions. I think you guys did really good. We still have 10 minutes if you guys have questions as you're picking up, but I think we can end early today.